Hi everyone, this is Mrs. Leong, and I'll be going over lesson 2.6 part B on special functions. All right, so our main objectives for this lesson is to be able to graph two special functions. One is called the step function, and the other one is the absolute value function. All right, so we're going to start with what I think is the harder one, which is step functions. All right, now to be able to graph these step functions, you need to know what this notation means. So this is the notation for the step function. This is also known as the greatest integer function. All right, so I'll go ahead and write that up here. This means the greatest integer function. Now, let me go and explain what that function does to a number. So in general, it means you want to find the integer closest to what is inputted into those brackets, but without going over. So it can't be above. So let me go ahead and give some examples for what that means. So let's say I put 2.1 into this function. I want the closest integer without going over. So the closest integer to 2.1 without going over is 2. Same thing if I do 2.5. Closest integer, but without going over, is also 2. Even if I have 2.99999, closest integer without going over is still 2. All right, so that is what that function does. Let me give a few more examples. Let's say 0.9. All right, so closest integer without going over would be 0. 0.01. Closest integer without going over, 0. Even if it's an integer itself, you would just say closest without going over is actually just 0 itself. All right, the goal is not to go above. It gets a little tricky with the negatives. All right, so let's practice a few negatives. So negative 0.1, closest integer, but without going over. If I put 0, 0 is greater than negative 0.1, so that would not work. Instead, the closest integer would be negative 1 without going over. Negative 8.2, closest integer without going over would be negative 9. I can't put negative 8 because negative 8 is greater than negative 8.2, so that would be going over. All right, and I'll just do one more example. And that will be equal to, think for yourself what you think that's equal to. And hopefully you thought negative 3. Okay. So this ends up giving a very interesting graph, as you can tell. What happens is, ends up looking like a step, all right, or steps, a little staircase here. So that's why it's called a step function. The reason why is because on the integer, like we put 0 in, right? Put 0, we got 0. If you did 0.1, it would still be 0, 0.2, 0.3, 0.4, all the way to 0.9999999. The output would be 0 until we hit exactly 1. All right, once we input 1, then we get an output of 1. And then same thing, 1.1, 1.2, 1.3, 1.4, all the way to 1.99999 would give me an output of 1 until I hit 2, and then it would jump to 2. So that's why we end up getting these steps. All right, so this is what we call the parent function. This is the most basic graph where it is just the graph of this step function and nothing else. All right, so this is the graph of that. All right, once we have that basic parent function down, we can play around with it. All right, so here are the different things we can do to that function. We can multiply inside the function. We can add or subtract inside the function. We can multiply outside the function. We can add outside the function or subtract. All right, and these are what happens when we do those things. All right, so let me go ahead and show you. I'm going to jump around a little bit here. All right, so let me start with the horizontal shift first, actually. Let me start with this one. All right, so when we add or subtract inside the function, it's going to shift horizontally. All right, and the horizontal shift will be this much. For me, it's hard to kind of remember that negative c over b. So I think this. For the horizontal shift, set whatever is inside those brackets to 0, and then solve for x. And that will tell you your horizontal shift. All right, so let me show you an example. I'm jumping to example 4 for this one. So example 4, I see that something is being added inside my function. That's how I know it's a horizontal shift. To figure out the horizontal shift, I'm going to set whatever is inside equal to 0 and solve for x. So since x is equal to -1, I know I'm going to have a horizontal shift 1 to the left. All right, so horizontal shift 1 to the left. All right, so I'm basically going to take my original parent function, this whole thing, and I'm going to shift everything 1 to the left. All right, so that's going to look like this. I usually start with the origin point, and then I just copy everything else around it. All right, so go ahead and just graph all the way to the ends. This just keeps going on forever. Okay, and that is your graph. Okay. We'll do domain and range a little bit later. So we'll hit up domain and range in just a sec. Let's get the graph first, okay? All right, and that's it for the graph for number 4. All right, so that is your horizontal shift. Set whatever's inside those braces to 0 and then solve for x. Okay, let's do a vertical shift. So vertical shift is this one, where we add or subtract outside the function. All right, horizontal was when it was inside, vertical is when it's outside. This one's pretty straightforward. It's just whatever is out here, that is your vertical shift. So for example, number 1, I can see subtraction of 2. So I'm going to shift from my origin down 2. So that's going to be my new starting point. And then just go ahead and graph the rest. Okay. And that's the graph for number 1. All right, let's try our next one. Let's do the multiplication inside the function. Once again, if it's inside the function, it's going to be horizontal. All right, there's going to be a horizontal change. So this 1 over b, so the reciprocal of that, is going to be the horizontal length of each step. Okay, so let me go to example 3 for this one. All right, so this is the same thing as 1/2 x. And since b, in this case, is 1/2, the length of each step is going to be the reciprocal of that. All right, so since b is 1/2, 1 over b is going to be 2, and that's going to be the length of each step. No shifts, so I still start at the origin, but now each step is not 1 unit long, it's 2 units long. It's going to look something like that. All right, and if you don't feel comfortable having those float, it's okay to just leave it like that and just assume that the rest keeps going. Okay, so that's it for number 3. And lastly, let's go to our multiplying outside the function. All right, and that is this guy right here. And it's just how much higher the next step is. Okay, and that's assuming a is positive, a is negative, then it'll go in the negative direction. Okay, kind of like a slope. So example 2. A in this case is 2. All right, so that's A. No shifts, so I'm going to start at the origin. And I'm just going to go 1 for the length. since there's nothing multiplied inside, it still stays 1. But when I get to my next step, I'm going to jump 2 up instead of 1 like I usually do. So 1, 2, and then I'm going to create my next step. Go up 2, create the next step. And that's it. Okay, so those are the 4. This is what we call transformations of the graph. Let's talk about some domain and range now that we have those transformations. All right, for these, I'll just let you know domain is pretty much all real numbers. As I scan along the x-axis, I have graph everywhere. There's nowhere I don't actually hit graph. So this is going to be a domain of all real numbers. Actually, I'll just do that symbol right there, all real numbers. The range is a little trickier. I don't have graph everywhere. I only have graph here at these steps, these specific lines. So I cannot say all real numbers because no decimals, just these numbers here on the number line. Well, good thing we know that that number set is called integers. So I'm going to say all integers for the range. All right. This one, domain, once again, all real numbers. The range, I have these numbers that have graphs along the y-axis. So 0, 2, 4, -2, -4. These are even integers. So I'm going to say all even integers for the range there. All right, here, domain, again, I have graph everywhere along the x-axis, so all real numbers. And then for the range, this one, I hit 0, I hit 1, -1, -2, so all integers for this one. All right, and then lastly, number 4, this one, I have all real numbers for the domain. For the range, looks like it's once again all integers. All right. So those are the domain and the range. Okay. Let me show you for number 5 what it can look like when you have multiple transformations, and then I'll have you guys practice with number 6. All right, so for number 5, when I have multiple transformations, I'm gonna go ahead and see that this is like A, is gonna affect how high the graph is gonna jump, and this right here is gonna be a horizontal shift. All right, so let me go ahead and shift. I'm going to set that equal to 0. And I see x is equal to +3. So that's going to be my new starting point. Since nothing is multiplied in front of the x, I know the length of my step is just still going to be 1. And then because of that 3, I know I'm going to jump up 3 to get to my next step. And then down 3 to get that step. All right, so there's my graph. And then domain, all real numbers. Range, I'm hitting 0, 3. I have graph at -3 and -6. All right, so it looks like just integer multiples of 3 is how I would describe that. So all integer multiples of 3. I'm also definitely okay with you guys just doing, let's do like ... -6, -3, 0, 3, 6, ... Just showing that pattern. If you want to write it in that way, I'm okay either this way or this way. All right, why don't you guys go ahead and try number 6. So pause the video, and once you're done, you can go ahead and check and see if you got it. Okay, let me go ahead and see if you guys got number 6. So final answer here, this is what I would do. I would set that equal to 0. Solve, I get 5/2, so basically 2.5. So that's my new starting point here. And also because of that 2, this is my b, I know my 1/b is going to be 1/2. So that's going to be the length of my step here. So half length, like that. All right. Nothing is being multiplied out here, so I'm just going to jump up 1 and do halfway, jump up 1, halfway, jump up 1, halfway, jump up 1, halfway. All right, and then same thing, going the other way. All right. And then hopefully you didn't forget domain and range. Domain would be all real numbers, and range would be all integers. All right, and that is step functions. Okay, that was the harder of the two, okay? The easier of the two is absolute value functions, all right? So your absolute value function is gonna look like, this is your parent graph. This is 1, 1, negative 1, 1, and it looks like a V like so. Okay. So that is your parent graph, just a V. And I'm going to treat this just like kind of the step functions, those transformations. All right, so if I want to graph this, same thing. Inside the function, I'm going to set equal to 0. I get x is equal to negative 1. That's a horizontal shift to the left 1. All right. And then now this right here is kind of like a pseudo slope. Pseudo slope. Which means it's not really the slope, but you kind of treat it like the slope. All right, or it acts just like the slope. Go down 2 over 1, down 2 over 1. You'll get this side. And then just mirror it on the other side to get that V. All right. And if you're not confident with that pseudo slope, you can definitely plug in numbers. So I would still first find that negative 1 and then just plug in numbers around it, right? Substitute in numbers around it, and then you could get that same graph. So either one I'm okay with. All right, domain along the x-axis, I have graph everywhere since it goes forever to the left, forever to the right. And then the range, I have graph from here all the way down. All right, so it starts at 0 and it goes below. So y is less than or equal to 0. All right, and that's how you graph absolute value function. All right, why don't you pause the video again, try number 8 on your own, and once you're ready, unpause, see the answer. All right, so here's the answer. Setting x, the inside to be 0, it's just 0. So when I plug in 0, just go this route. When I plug in 0, I get negative 4. If you kind of want to do the transformations, I have no horizontal shift, but I have a vertical shift, down 4. So that's why we have a kind of middle point right there. And then you can use your pseudo slope. You can go up 3, over 3, up 3, over 3, and mirror on the other side. Or if you're not super trusting of that, you can definitely plug in the numbers and get the same answer. All right, so you're going to put something like that. Okay, don't forget domain and range. Domain in this case, all real numbers. Range, y is equal to negative 4. Okay, and that is how you do absolute value functions. Okay, our last problem here, a word problem, just to show you how step functions can actually pop up in a real life situation. It's not this random thing a math person just conjured up. So number 9, Springfield High School Theater can hold 250 students. The drama club is performing a play in the theater. Draw a graph of a step function that shows the relationship between the number of tickets sold, X, and the minimum number of plays, Y, that the drama club must perform. All right, so they already tell us that this is going to be the number of tickets sold on the X, and then the number of plays is going to be on the Y. Okay. And now we just kind of need to, excuse me, understand the situation. So the theater can hold up to 250 students. Okay. So now if, let's say, we have 0 people coming to the theater, we're not gonna have a play. All right. So let's pretend though that, I don't know, 10 people show up. Well, we're gonna have one play. Even if there's one person, we're gonna have the play for them. So we're gonna have a play for them all the way, one play, all the way until we reach max capacity, which is 250 people. Okay. But if more than 250 people want to see it, then we're going to need to do a second play, all the way until we hit a max of 500 people for those 2 plays. All right, and then hopefully you guys see kind of where this is going. All right, so that would be your graph, et cetera, et cetera. And you can go as far as you want with that, but I'm just going to go ahead and stop there. Okay, so hopefully you guys see that. It can actually apply into real life situations, these graphs. Okay, good job. And that is it for lesson 2.6b.